Welcome to Cimerix. The following is a demonstration of what the multi-phase module in the Cimerix virtual testing code PumpLinks and Cimerix MP is capable of. I will list some typical applications for which the multi-phase module is useful for modeling gas-liquid interface movement and the motion of the interfaces between any number of immiscible components that are included in the simulation. Here is a validation case of flow over a weir. You can see that the predicted shape of the free surface matches experimental data almost exactly. This is another validation case of a volume of water initially static but then released to flow under the influence of gravity. This is the dam breaking problem. We see a comparison of experimental visualization versus a PumpLink simulation. The predicted free surface matches quite well to the photos of the experiment. Here we have the classical tank sloshing problem. The liquid movement is driven by time-dependent accelerations on the container, simulating a box half full of liquid, which is moving. The liquid volume is conserved, surface tension is included, and the gas, which is air, is compressible, modeled using the ideal gas law. Here is a view where the liquid is transparent so that any internal free surface structures can be seen. Here is an automotive application, gearbox splashing. The gear teeth shape is preserved, micro-sized clearances are modeled. We use rotating, sliding, and deforming meshes, and again, liquid volume is conserved, and the air is compressible. At 150 RPM, we see that the liquid, which is oil, is scooped up by the gear teeth rather gently as gravity dominates the system.
A tank sloshing model in Cimerix. So before we get into it, I just wanted to give you an overview of the model we are going to set up. As you can see on the screen, this is the model of a tank, which is partially filled with water and rest of it is filled with air. And we are just going to be displacing this tank. It's going to be an oscillating motion along the y direction. And the idea is to to predict the flow patterns and to study the sloshing inside of the tank. So let's get into it. So to begin with, what I have here are the CAD surfaces of the tank, which you can bring in from any CAD package in STL format. And just to get a sense of the dimensions of the tank, basically along the y direction, which is the biggest dimension here, it's about 0.9 meters in length. And in the x direction, which is the thickness direction, it's about 0.1 meters. So fairly typical of a fuel tank inside, inside of our automotive vehicles. And to begin the model setup, the first step is to generate the mesh. So we go into our general mesher, and then we are going to add these surfaces. And we're going to use a relatively coarser mesh size for today's demonstration purposes. But at the same time, something that will give us fairly reasonable results. And then we're going to generate the mesh, and in a jiffy, you can see that the mesh has been generated. We're going to just do a quick inspection of the mesh to make sure everything looks good. And we'll double check the cross section. So it's a fairly reasonable mesh, right? The total cell count is about 134,000. So relatively a really small model compared to the size of models that we run these days. Next, once we have the mesh generated, the next step is to assign the physics modules that we need to solve for in this simulation. So this is a classic multiphase VoF problem where we have two fluids sloshing. So I'm going to include the multiphase VoF solver. I'm also going to add the turbulence model to account for all the turbulence that occurs due to the sloshing. And with that, I think, yeah, we are good with the flow physics. And quickly, we are going to set up the numerics for this flow module, our best practice is to use second order upwind for the numeric scheme for better accuracy. And also we want to include the effect of gravity. So I'm going to turn the gravity force on, which is going to be downward, so minus Z. So I'm going to specify a value of 9.81. Next, I'll move on to the multiphase module. So by default, Simerix adds two components to the multiphase model. So I'm going to rename this to air, and the second fluid is going to be water. And we are just going to use the default settings in our multiphase solver. So we use the explicit scheme. We have the Courant number set to 1, and we use this adaptive Courant number method where we cut off the Courant number at maximum Courant number at 10. And next we'll go on to the turbulence model. Turbulence model, pretty much we use all the default settings. I would just change the convergence criteria to 1 because we are mainly interested in solving the flow parameters to converge to 1. Turbulence usually does not play such a big role in convergence. So having done that, the next step is to assign the material properties. So we select the tank volume, and over here in the properties panel, I'm going to assign the air properties. In this case, it's going to be a constant density of 1.23 kg per meter cubed. And for the water, I'm going to assign a density of 998.2. So fairly typical values. And then coming on to the flow module, we need to set the viscosity. So for air, we're going to set a value of 1.8 E minus 5. And for the water, it's going to be 0.001003. Again, standard values at typical standard conditions. And we are also going to include the effect of surface tension for water. And the surface tension is going to be 0.073 Newton per meter. Lastly, we are going to come into this multiphase to define the initial condition to initialize our domain with water and air. So I'm going to initialize with a value of A0, which is basically an expression to define the level of air, and W0 for water, which I had already populated inside of this expression editor. So it's a fairly simple expression which just defines a Z coordinate above which it's going to be water, and below this level it's going to be water, and above that level it's going to be air. So it's a fairly simple expression here. And yes, after initializing the domain, we are pretty much set with our volume conditions or assigning the material properties. Next, we need to assign for the motion of the tank. So to do that, we are going to use this volume remesh option, and we are going to use the displacement, or rather the translation option, and we're going to provide a displacement to this tank, which is specified by this variable here, which is nothing but a very simple expression again, which is just an sine function with a certain amplitude and a frequency. So it is a function of time. So it's a reciprocating motion. It will move from left to right and so forth. And also, this volume remesh only takes care of the mesh motion. We still need to provide the actual velocities on the wall so that we can account for the shearing effect on the fluid. So to do that, we select the boundaries, and in this wall kind of boundary condition, it's we're going to change the stationary wall and specify a Cartesian velocity on this wall. So we're going to assign a velocity of Vy, which again is nothing but just the differentiation of this displacement so that we get the velocity. Again, a fairly simple expression. Having done this, lastly, we just want to enable some outputs. So I normally like to enable most of these integrated values. It just helps us, to give more insight into our simulation. And also, it helps us to maybe cross-check to make sure everything makes sense. So I'll just enable some, common outputs, which will also help us check for the masses of different components inside of our domain. All right. Yep. I think with that, we are pretty much set up the model. So just to quickly summarize, we started with the CAD surfaces. We generated our mesh using the general measure option. And then we just add all the physics modules that we want to solve for. We define the two fluids that we are solving for. And then we assign the material properties for the two fluids, which includes the density, viscosity, surface tension, and also the initialization of our domain. And lastly, we assign the velocities. And next, we are ready to run the simulation. So this is going to be a transient simulation. We are going to run it for 14 seconds with a total number of time steps of 2000. And number of iterations per time step, we're going to leave it at 10. And we're going to save the results every 50 time steps so that, we can create an animation. And before we run, let's quickly save this project. I'm going to save it as with today's date, May 3rd, and we are ready to run the simulation. So you can see that the simulation has already started running, and I'm going to quickly create an ISO surface to see the volume fraction of water. All right. I'm going to hide the CAD surfaces here. And then let me give a realistic color to the water. And then add some transparency so that it looks better. We can see through it. Maybe I can plot the pressure on it. All right. So you can see, I'm just going to leave my cursor here. You can see the tank moving, to the right. And as the tank moves to the right, you can see the water sloshing to the left. So this model can run really fast. You can see I'm running on it's a desktop with 32 cores, and it runs really, really fast. So in about a minute, it completed 1 second of, the simulation, and we just need to run 14 seconds. So it takes about 14 seconds to run. So while the simulation is running, I quickly want to go through some validations that we have for this particular model. This is actually a paper written by the folks at University of Naples in Italy, and they had it in collaboration with Fiat Chrysler Automotive in 2018. So they actually had a test bed that looks exactly like the model we set up here. And of course, for that model, they used a relatively finer mesh, but still it was, the total cell count was about 1 million. And they did some comparisons for this model. So I'll quickly go through these images here. And over here, they're comparing the isosurface of water as a function of time at different instances of time, and compared that with the experiment. So as you can see, at different intervals of time, when the water sloshes from right to left in all the different scenarios, the isosurface matches pretty well to the image from the test. Right, this is some pretty significant sloshing, and we capture these patterns pretty well. And in addition to this, they also did some comparisons, some quantitative comparisons where they measured the center of gravity of the fuel tank, and they compare it with the experiments. And you can see that the two curves basically, line up pretty well. We get pretty close agreement between the experiment and the simulation. And all of this simulation was done inside of Simerix. This is for the X displacement, horizontal, and this bottom plot here is for the vertical displacement. And they did the test at two different frequencies, at 0.5 hertz and 0.7 hertz. So we get fairly good agreement. And the overall standard deviation was about 2.2% for the center of gravity. And in addition to this, we also compared the free surface of the fluid. So we just extract the top free surface curve and plot them for the experimental versus the numerical result. And again, the two curves were quantified by outputting the standard deviation, and the error was within 4.2%. So we get pretty good agreement even for such a small such a small model, and it runs really quickly. They ran the simulation in like in 2 hours. So we are able to produce really good results in a really fast time. All right. Yeah, I think that completes this demo. I'll hand it back to Chirant.
Yeah, thank you, Varun. Let me